SwayamPrabha. Digital India. Educated India.
Okay, so let us continue what we discussed in the previous class. So today we are going to discuss briefly about strain rate sensitivity. We are going to continue, this important property which we can evaluate from tensile test of a sheet. So strain rate sensitivity, as the name suggests, this parameter is going to tell us about the how sensitive is the material's deformation or flow stress with respect to the strain rate. So generally, the rate, as it is, said in this term. So the strain rate means it is defined with respect to some time, isn't it? So now this strain rate can also be related to cross-head speed. Okay, so strain rate is generally given by V by L. Okay, and this is a true strain rate, epsilon dot. Okay, so epsilon dot is nothing but V is nothing but your cross-head speed. You can see here V is nothing but the cross-head speed, the speed at which you deform the material. Okay, and L is nothing but your the instantaneous gauge length, because this is a true quantity. You are going to have instantaneous gauge length. Okay, so V, you can say for example millimeter per second divided by millimeter. So unit is of strain rate is nothing but second inverse. Okay, so strain rate is defined by V by L. Okay, so where V is nothing but your cross-head speed and L is nothing but instantaneous gauge length. Okay, so now how sensitive is your flow stress or deformation, okay, with respect to change in strain rate is what will be quantified by strain rate sensitivity. But generally you will see that at room temperature, it is generally said, okay, at room temperature material will not vary in its properties with change in speed, okay, or strain rate at which tests are performed. Okay, generally. But suppose for example you have a stress strain behavior like this, okay, and you are starting your deformation, of course, from zero strain, and then you are deforming it. I just drawn it in the plastically deforming zone. You will see that you are deforming it in one particular strain rate, epsilon 1 dot. Okay, so here we are saying epsilon dot now, so here it is epsilon 1 dot. You are deforming it in one particular strain rate, and you are suddenly changing the cross-head speed. Let us say for example you are changing the velocity by 10 times. Okay, so accordingly there will be some change in the strain rate. Okay, and you are continuing your deformation like this, and let us say for example you are coming back to your original strain rate and you are completing your test. Okay, so basically there is a jump in the cross-head speed V. Okay, or equivalently you can say that if V is changing, epsilon dot may also change. So you are taking the strain rate from epsilon 1 dot to epsilon 2 dot. Okay, and there will be a corresponding change in sigma 1 and sigma 2. Generally flow stress changes like this. Okay, when you strain rate, when you change it from epsilon 1 dot to 2 dot, sigma 1 or flow stress is changing from sigma 1 to sigma 2. Okay, so this is going to be the effect. Okay, suppose if you want to capture this effect, okay, then you have to slightly modify the flow stress model, which was initially sigma is equal to k epsilon power n. Now I am going to include one more part, epsilon dot power m. Okay, epsilon dot power m. Okay, and this exponent is very important, which is going to tell you the effect of your strain rate, and it is called strain rate sensitivity index. Okay, like you have sigma, which is nothing but flow stress, and or true stress, and epsilon is true strain, which you have seen yesterday's class, k strength coefficient, n strain hardening exponent, we know that. Now we are going to add include this one more part, epsilon dot power m. Okay, where m is going to tell you, m is actually called as strain rate sensitivity index m. Okay, so how do you calculate this m, which is going to tell you what is the effect, okay, which is what is given in this diagram. Of course, this diagram already explained you. If you change the strain rate from epsilon 1 dot to 2 dot, then there will be a slight change in flow stress from sigma 1 to sigma 2, and m can be calculated using this equation. Okay, you can say m is equal to log sigma 2 by sigma 1 divided by log epsilon 2 dot divided by epsilon 1 dot. Okay, So where sigma 2, sigma 1 and epsilon 2 and epsilon 1 are the corresponding change in strain rates and flow stress. So this like M also affects the forming behavior, okay. So which we will see in next few slides. So now I am moving to effect of these properties. Okay, so for the last couple of slides we are seeing how to calculate the load displacement graph. Okay, we start with load displacement graph, then we have engineering stress, engineering strain graph, when sigma versus epsilon graph. Okay, so from this we can get several properties. For example, your yield stress, UTS, uniform elongation, okay, total elongation, then n value, k value. In the last slide we have discussed how to calculate m. So all these things can be calculated, but what are this effect? Other than that, you have plastic strain ratio, which is going to quantify the anisotropy of sheets, and this plastic strain ratio we said can be represented as R bar and delta R. So what is the effect of all these parameters, which we are going to see in next couple of slides in a very brief manner, and in other than this slide, in other part of the course also you will see the effect in a different manner. So strain hardening, if you see, okay, so this is actually a critical factor during plastic deformation, okay, isn't it? Because only because of strain hardening you will see there is a jump in flow stress from between yield strength to UTS, okay, and in a way your strain hardening exponent n is going to quantify how hardening the material is going to be. Okay, so it is generally understood that higher the strain hardening of the sheet, better it will perform in process with significant stretching. Okay, wherever you have stretching, okay, there you need to have sufficient strain hardening in the material so that stretching can happen in a very successful manner. Okay, so suppose for example you pick up n, what is the effect of n? Okay, we will see the effect of n in due course in other chapters also, but you will see that the effect of n, if you want, you can directly discuss connect it to, you can say, strain distribution. Okay, strain distribution means what? We will elaborately study this in next couple of slides. Strain distribution means what? Suppose you deform a material, okay, deform a sheet, okay, like I have deformed a sheet like this. Okay, so I am going to calculate strains at each location in the deforming zone and in the undeformed zone. Of course, in the undeformed zone there will be not much of strain distribution, but from this portion to this portion there will be strain distribution, right. So what is strain distribution, how to calculate, we will see in due course, but it is generally understood that there will be some strain distribution here. Okay, that means your strain is going to get distributed in a uniform and in non-uniform way depending on how much displacement you have given here. Okay, so as long as the strain is uniformly distributed, okay, so you will see that the material will not undergo tearing or necking, and n is going to be helpful for that. Okay, and n is going to be helpful for that. So larger the n, okay, let us say for example you have material with 0.3 n, okay, 0.3 n value. There is another material you have 0.2 n value, and this 0.3 n value, this material is generally preferred from formability point of view. Why? Because you may have uniform strain distribution from this point to this point for higher n value, which also means that you can delay instability or necking. Okay, so now if you want to look into effect of sigma ys, that is yield strength, okay, generally it will not affect the deformation behavior directly, except that the sheet is difficult to deform, okay, depending on what yield strength you have. So larger the yield strength, it's going to be little bit difficult to push it plastic deformation. Okay, and your total elongation, E total or epsilon t, okay, and uniform elongation, let us say epsilon u. Okay, I think you also know the fact that this uniform elongation is generally related to let us say for example I am just drawing here. Okay, so you have sigma versus epsilon graph, okay, you have like this. So epsilon u is related to this and epsilon t is related to this particular point. Okay, so when epsilon u is large, let us say yield strength is here, okay, epsilon u is large and epsilon t is also large, means okay, you have greater strain hardening ability to that material. That is one way can be connected, and this epsilon u t can also be connected to n, that you will study in due course. Okay, so you may say that your if n value is larger, epsilon u, okay, where your UTS is reached or instability is going to start, that will also be little large. Okay, so that your necking is actually delayed. Okay, so your then comes your elastic modulus. So Young's modulus, it can also impact the performance. Mainly greater the modulus, it is little stiffer to deform the component, okay, which is usually advantageous. And this modulus will also affect spring back, that I was discussing with you yesterday. Okay, so that modulus will influence the spring back when forming. Spring back, I think you understand. Okay, there will be recovery of some dimensions once you remove the load. That is because of some elastic properties. One important property is your Young's modulus. It is generally understood that a lower Young's modulus results in bigger spring back, and in general it is going to create more trouble in controlling the dimensions. Okay, so you have to be a little bit careful with respect to the modulus of the material in this way. Okay. So while choosing the materials, sheet materials, one has to look for all these properties. Okay. So what n value it's going to have, sigma ys, how is it? Okay. Then this n can also be connected to uniform elongation and total elongation. Okay. And then your the other one comes your E. Okay, Young's modulus. Okay, all these parameters are connected to the selection of material for a particular application. So now comes the anisotropy. Okay, in the previous section we have discussed how to quantify anisotropy. Say for example, you take a sheet, any aluminum or steel sheet, and assume that this is the rolling direction of the sheet. I am just drawing RD. Okay, and what do? You take a rectangular strip like the way I described in yesterday's class, and by known procedure you can get a plastic strain ratio. What is plastic strain ratio? It is true width strain divided by true thickness strain, so that you can calculate it in this direction. So it is going to be R0. R0 means the direction coincides with the rolling direction. So I am putting 0 for that. So you take the same rectangular sample. Rectangular sample, what I mean is this value. Rectangular sample means this particular sample I am referring to, right? So this sample, you are deforming it and you are calculating the R value as I discussed yesterday. So this is R90 going to be, and at any other angle you can pick up 45 degree, and this is also 45 degree, you will get R45 two times. This is one R45, this is another R45 you can get, and from R you can get R bar, okay, by using R0, R45, R90. Okay, so R bar, you know that it is nothing but R0 plus 2R45 plus R90 divided by 4 we said yesterday's class, and delta R is going to tell you R0 plus R90. So what did you say? R0 plus R90, you can say that minus 2R45 divided by 2 we said. Okay, so this also tells that this is like an average quantity, you can imagine, and I also told you that this equation you can use only if you have 3 loading directions, 0, 45, 90. Okay, and delta R is nothing but how different it is, the average of R0 and R90 with respect to R45. So R0 plus R90 divided by 2 minus R45 you can say. So how different is this with respect to R45 in a plane? Okay, on the sheet, how different is R0, R90 with respect to R45? That will give you delta R. So this is we say average plastic strain ratio, and this is going to be your your planar anisotropy. Okay, so now what are these effects? I think you understand now what is epsilon W, what is epsilon T. In the previous section we have described how to calculate it. Okay, if delta R is large, okay, either positive or negative in circular parts, asymmetric formation and earring will be noticed. Okay, so earring is actually a defect. Earring is actually a defect. Okay, so you can look into different resources. You will see that when a cup is formed, you will have this kind of waviness. You will have this kind of waviness at the edges. Let us say this is the cup edge. This is a circular cup you are made by deep drawing. Okay, this is a circular cup you are made by deep drawing. Okay, and you will see that this kind of waviness are seen at the edges. This is actually called as a earring problem. Okay, so this earring happens mainly because of delta R. Okay, so that means as long as there is going to be less difference between your R0 or R90 with respect to R45, then okay, your earring will be minimized. Your earring will be minimized. Okay, you have to be a little bit careful with this. Okay, so delta R is connected to earring. So a lower delta R, earring can be minimized. This irregular forming, no, so here it is drawn less, here it is drawn more. That's the meaning, right? So if you pick up this line, here it is drawn less, the height is more, and here the height is less, right? That is why you are getting this waviness, and that is because of the variation between this quantity and this quantity. Now when it comes to R bar, okay, So R bar is connected to this R, individual R values, right. So now a simple analysis will be helpful. So nothing but by T. Suppose I am taking R greater than 1, okay. Let us say R is equal to 2, okay. So epsilon W is equal to 2 epsilon T. That means what? That means you are giving deformation to the sheet and you are getting one thickness strain at a particular location, and width strain you will see it is twice that of your thickness strain, which means the thickness strain is smaller as compared to width strain, which also means that this implies that better strength in the thickness direction. That is why it is strained less as compared to width, okay, which also means that it has got good resistance to thinning, okay. So greater than unity, it means that greater than 1 unity, it means that thickness strain was greater than the width strain. This may imply that it has got better strength in the thickness direction, which also means that it has got good resistance to thinning, okay. Suppose if you take R less than 1, okay, which also means that epsilon W is equal to, let us say 0.5 epsilon T, okay, it is just opposite to that, okay. You will see that the thickness strain is going to be larger as compared to width strain, which also if you compare it with this, then this material is going to have less resistance to thinning as compared to this, okay. So here in this case your thickness strain is going to be larger, which means that in the thickness direction the strength is larger, okay, which also indicates that it is not so easy to make the material to thin down, okay, because it has got good strength, okay. The opposing effect is there in the thickness direction, okay. So which also means that a higher value makes it possible to draw deeper parts when drawing deeper parts, okay. Suppose if you want to draw deeper parts, then higher value of R bar, okay, either R bar or R, okay. We take a cumulative value, that is average value R bar, which should be larger, okay. So R bar has to be larger. Why? Because you have good resistance to thinning, and delta R has to be lower. Why? Because it has to you have to avoid this earring problem, okay. So now surface effects, these are all certain other parameters which will have some effect. For instance, sheet surface roughness, okay. So that will have interaction with lubricants, your tooling, it will have some impact on the performance, but it is very localized, so one has to look into it, okay. So but this cannot be quantified by tensile test, okay. So that is not possible, but it has to be taken as a separate quantity, okay. One has to really look into it when you have what is the the sheet roughness at that time, like that. But generally the sheet roughness, when you compare to sheet thickness, is going to be very, very small, okay. We speak sheet thickness of the order of 2 mm, roughness generally is of the order of microns, like that. So its effect is generally not much. Homogeneity generally it means, for example, you take thickness, okay. Suppose you take a 2 mm thick sheet, you measure at 100 different locations, it may not have same thickness at all the locations. So that may have some effect, okay. Similarly, your composition can slightly change here and there. Suppose you are taking tensile test sample and we expect that the gauge length, let us say we say it as L0, we should have uniform width, but it may not be, okay, it may not be. So that can create some heterogeneity in the material, that will also affect the formability. Strain rate sensitivity or strain rate sensitivity index, we connected it to M, isn't it? So M is also very important for you. So this M is like N. This M is like N. Okay. So like larger N is good for us, isn't it? That's what I told in the previous slide. Larger N is good because the strain distribution is going to be uniform in the sheet, and hence you can delay necking. Similarly, M also plays a bigger role in affecting the ductility. Okay. Positive rate sensitivity typically enhances forming and produces a result that is comparable to strain hardening. This is what I was telling you, and you will see that this M is going to be affect mainly the post necking behavior. That is what is generally said. This N is going to affect the strain hardening behavior, okay, but this M is going to affect the post necking behavior. Post necking behavior means between epsilon U and epsilon T. Okay, this epsilon T minus epsilon U increases with the strain rate sensitivity. Okay, what does it mean? It means that suppose if you pick up a stress strain behavior where we have seen that somewhere here, right? Yes, suppose you take this particular engineering stress strain curve, for example, I am saying, okay, this range, epsilon T minus epsilon U, this is actually controlled by M. This is actually controlled by M. Okay. Whereas before that, in the strain hardening region, N plays a vital role. Okay. That is the meaning. So, M and N are generally of that nature. Okay. So, larger M, larger N would be better for you to have better formability. So, epsilon T, it is, you can say epsilon T minus epsilon U also increases, okay, with rate sensitivity or sensitivity index, that is M, which is actually good for us. Before reaching epsilon U in the strain hardening region, N plays a role. Just after that, epsilon U before epsilon T, post necking behavior, okay, M plays a role. That is the meaning. In fact, there are materials called superplastic materials which follows a phenomenon called superplasticity. Okay, for those materials, if you see, M is going to be very, very encouraging. Okay, and that there are a lot of details one should go into it, and it may have ductility of the order of, let us say, 500,000% also if M is larger. Okay, so we will stop with this, and then now slowly we will do some problems, but quickly I will open it. Okay, so that we can complete this chapter and go to the next one. Okay. So, the first part which I was discussing is on introduction, right. So, that will not have any problem. Now, the second part where we have seen tensile, tension test and tensile properties, how to evaluate. There are a couple of problems I could bring here. So, these are all simple problems which will make you to understand this. Now, let us take a first problem Q1. Okay. So, Q1 if you pick up, so you will see that a tensile sample, okay, is cut from a sheet of steel of 1 mm thickness, right, from a sheet of 1 mm thickness, and the sample has got initial width of 12.5 mm and gauge length of 50 mm, right. So, you pick up a tensile sample, I just drawing the gauge length only, this gauge length they say it as how much, 50 mm, okay, and you will see that this width as 12.5 mm. And it has got a thickness of 1 mm. Let us say from the side view it is 1 mm. Okay. So, a sheet you can say like this. This is a gauge region only, no. So, I am just picking up like this. So, now the initial yield load is 2.89 kilonewton, Py is given, and extension at this point is so small, okay, 0.0563 mm. So, you can imagine that in a stress strain curve, this extension 0.0563, you may reach a yield load. So, this is a point to be noted, how small the dimension, the extension is going to be to get the yield load. Determine the initial yield stress and you need to get E, okay, that is your elastic modulus. So, how is going to be the first part? Initial yield stress is pretty straightforward, isn't it? It is nothing but Py by A naught, which you already discussed, Py by A naught, right. So, Py is the yield load and A naught is the initial area of cross section. So, you can directly use initial area of cross section from these dimensions. So, Py is already given 2.89 kilonewton divided by A naught. A naught is what? A naught, this fellow is 12.5 and your thickness is let us say 1 mm. So, 12.5 into 1 mm is 12.5 millimeter square. So, and you can calculate it. I just calculated, it seems to be correct. So, 231.2 MPa. So, you have to be careful with the units. This is a kilonewton per mm square, isn't it? So, accordingly you need to have units here. So, 231.2 MPa. So, it is very simple to calculate it. So, now if you want to go for elastic modulus E, okay. So, this elastic modulus E, if you want to zoom it, let us say in general stress strain behavior, if you want to zoom it, you can go like this, a little bit of I am writing. This is your sigma F0. Which is what is given here, right. So, now you need to get elastic modulus, which is nothing but the slope of this part, the slope of the initial part, right. So, I can directly write sigma F naught divided by the corresponding strain. Corresponding strain is what is E y or epsilon y, you can say. Okay. So, now sigma F is known to me, that is nothing but my 231.2, and what is Ey? Ey is not known to me, okay, because Ey is nothing but the x axis, which is nothing but your strain. So, if you want to calculate strain, you can go back to original definition, which is nothing but delta L by L naught, delta L by L naught, that we have seen in the previous slide. So, L naught is 50, that is already given here. Delta L you ought to get, and delta L is what is given as extension at this point is 0.0563, which you are substituting here, and you will get such a small strain. You can imagine that how small it is, 0.00112. Okay, by that time, it actually crosses the yield point, that is the meaning, 0.00112. So, that you substitute in the denominator, and 231.2 divided by 0.00112 will give you Young's modulus. Generally it is represented in GPa, generally is represented in GPa. So, yield strength in MPa, strain you know that it has got no unit, mm by mm, and Young's modulus generally represented in GPa. It is 205.33 GPa. Okay, and this is, you can imagine that 205.33 is like for a typical steel. Generally we use 210 GPa like that. Okay, and you can see that it is also given in the question. This could be a real data which people might have evaluated. So, one has to be careful in that also, and we will get some idea of how the value is. Now, let us go to part B. Now, part B is about calculating R value, that is your plastic strain ratio, which is going to quantify anisotropy of the sheet. So, when the extension is 15%, they have already given extension is 15%, width of the test piece is 11.41 okay, mm, okay, 11.41 mm, okay, you can say. You have to determine the R value. So, R value is known to you. So, R value is nothing but true width strain divided by true thickness strain, that we already know, which is what is I have given here, ln of W by W naught divided by ln of W naught, L naught divided by WL, okay, and this also we derived in the last class. Okay, so, this is nothing but ln of T by T naught, and this T by T naught can be connected to width and length, instantaneous length and original dimensions in this way. Okay. So, now it is all about substituting the values which is given in this particular problem. So, now there is 1.28 that your new width is already given, the width of the test piece when the extension is 15 mm. That means, let us say for example, you take this gauge length, okay, which is 50 mm, okay, and it is increased to one particular length which is going to give you 15% extension. At that time you will see that this width is something and this width is reduced, isn't it? This width is reduced. Let us say this is 12.5, it is given, that has become, this fellow has become 11.41, right? But this fellow is not known to us, this fellow is not known to us, okay, this dimension is not, but then strain is given, you have to convert that. Okay, so that we will do it here. Okay, so W is given 11.41, initial W naught is given, that is 12.5, which is already noted here. Ln of W naught you already know, L naught is gauge length 50, W is already know 11.41, and this fellow your L, okay, this L naught, no, it has become L, no, this length you need to get, this length you need to get. So, for that you have got 15%. So, you have to see that 15% means, let us say 0.15 would be equal to delta L divided by your L naught, and into your L is 50, let us say it is going to be your probably 7.5, and you add it with 50, it is going to be 57.5. That is a new length. That is a new length. Okay, this new length L is nothing but delta L plus L naught. No? So, L naught is 50. Okay, this delta L is what you will get it from this 15%. Okay, so you need to get this for what new length you will get 15% strain. That is the meaning. So, for what new length of this 50 you will get 15% strain, that will be 57.5. You can calculate it and check it, and if you substitute all these things and properly calculate, you will get R value as 1.88, which means that actually this steel sheet is actually anisotropic in nature, because it is not equal to 1, it is greater than 1, it is anisotropic in nature. Okay, and it has got good resistance to thinning. You can make deeper components with this. Okay, these are all some simple problem you can imagine, and let us go to the next one, okay, which is also relatively easy for you when you do tensile test. Let us say Q2. So, what is the question? At 4% and 8% elongation, the loads on a tensile test piece of an aluminum alloy are 1.5 kilonewton and 1.66 kilonewton. Okay, so you take a stress strain behavior, let us say sigma epsilon, and I am just drawing typically like this. Okay, so at 4% elongation and at let us say 8% elongation, very closer to that. Okay, this is in percentage, let us say elongation. The loads are given. Okay, this fellow is going to be 1.59. Okay, anyway, load is given. I am just written it as stress, that you will see 1.66. So, you can take it as P. Okay, you can take it as P. and maybe its elongation is given now, let it be strain, no problem. Okay. So now what is the question? Dimensions are given. The width of the sample is 10 mm, thickness is 1.5, gauge length is 50. So you can always draw a diagram like this, okay, and the thickness is this cross section. So thickness is 1.4 mm, and this fellow is going to be a 50. Again, gauge length is 50, and width is, let us say, initial width is, let us say, 10 mm. Thickness is 1.4. So what is the question? You have to calculate K and N directly. You have to get K and N directly. So how will you proceed actually? So let us go ahead with N. Okay. How do you calculate N? So N, as we discussed in the last class, you will say that N is nothing but when you draw a graph between ln of sigma and ln of epsilon. Okay. So you have a load displacement graph, you have engineering stress strain graph, and you have true stress strain graph, and then engineering stress strain graph, and then true stress strain graph. From this you get ln of sigma, ln of epsilon. So you can directly get this, and then you can get this, right? And this generally you plot it in the strain hardening zone. That's what I was telling you. So you get a straight line. Slope of that is nothing but your N value. That's what we discussed in the last class. If you remember it, we derived this equation, no? Ln of sigma is equal to ln of k plus n ln of epsilon, isn't it? That's what we discussed, right? So now, so if you want to get the slope of this, so you can write ln of sigma a minus sigma b, and the corresponding strains epsilon a minus epsilon b, isn't it? So there will be, you take two y coordinates and two x values, and then you can get a and b point are these 2 points. A and B points are this point and this point, the corresponding sigma values. Correct. So this will give you my ln of sigma a minus ln of sigma b divided by ln of epsilon a minus epsilon b. Now the question is, how are you going to calculate sigma a, sigma b, epsilon a and epsilon b? So n is nothing but a slope of a graph between ln of sigma and ln of epsilon. That's all we are saying. Okay, and you pick up any 2 point, you should be able to calculate n value accurately. Okay, and that's what we are giving here. The 2 points are already given in the problem. One is at 4% elongation, other one is 8% elongation. Okay, so now how are you going to get sigma a, sigma b, epsilon a, epsilon b is the main question here. Okay, so now sigma a, let us directly go to the formula. Sigma a is nothing but you can write PA by instantaneous area of cross section. Instantaneous area of cross section you want to find, you can connect it to your original dimension, which is nothing but LA divided by A naught L naught. So basically A naught L naught is nothing but LA AA. Okay. So instead of AA, I am putting A naught L naught into LA. Correct. So now all are known to us. We have to just calculate it. Okay. PA is already given to you, which is nothing but 1.59 kilonewton, and A naught. What is A naught? Initial area of cross section, isn't it? So it will be 10 into 1.4, isn't it? So which means 14, right? So and L naught is 50, fine. Now 52 you get. 52 you get because it is 4% elongation. Because it is 4% elongation. 4% elongation means what? 50 has to become 52 to have 4% elongation. Okay. So then you can calculate it. Okay. So I hope it should be correct, and accordingly you will get 118.11 MPa. Right. So now correspondingly you get a true strain at the A point, which is nothing but LA by L naught, ln of LA by L naught. Directly original definition of that is you can get. What is LA? LA already calculated. I think 52 divided by L naught is 50. So you will get true strain as 0.0392. We can say 0.04. Okay. Same calculation, do it at 8% elongation. Okay. Load is going to be different. Initial dimension is going to be same, 14. Length is also same. Only thing is 8% strain. Okay, 8% elongation, so 50 will become 54. Okay, so that you can substitute here. You will get, of course, a larger stress because of strain hardening. This is the meaning of strain hardening, right? When you move from point A to B, you need larger load for deformation, correct? So you need 1.66 here, okay, as compared to 1.59 here. So there is an increment in load, which is also reflected in sigma A to sigma B, which is nothing but because of strain hardening. Okay, so 128.06 you will get. Epsilon b, ln of LB by L naught. So L naught remains same, only LB is going to change 54. So you will get a naturally larger strain here. Okay, it is 0.0769. So, all are known to you. Okay, so you can just substitute it here. So, what is n? N is nothing but the slope of a logarithmic plot of sigma versus epsilon. The slope is nothing but you pick up one point, get this value which you already calculated, and this point you already calculated, correspondingly there is one point here already calculated, correspondingly you have one point here already calculated, and you go and check it. It is going to be ln of sigma a, that is 118.11 minus ln of sigma b, 128.06 divided by ln of this epsilon a, and then epsilon b, you will get n as 0.12. Okay. So, you can also understand a typical value of n. Okay. So, 0.12, 0.2, 0.25, the better the n value, it is better for formability. Okay. In due course, you will understand that. And how do you calculate k? Okay. So, k, this n and k, actually you can calculate it better from a full stress strain behavior. If you have full stress strain behavior data given, okay, ln of epsilon this, then between your yield strength to UTS equivalent of true stress, you can calculate the slope, okay, and it will give you n, and then your intercept, okay, will give you like here. Yeah. So, this point you can keep it as 0. So, now so that your sigma becomes k, right. So, k can be obtained. Now, but here you have got only 2 points. Okay. So, here you have got only 2 points. This is one way to calculate k, but then one should not use this method of calculating k, better to use it from the full stress strain data like we have described previously. So, this k is obtained from this equation only. So, the previous the part of this equation is sigma is equal to k epsilon power n, which we discussed in the previous class. So, k is sigma by epsilon power n. So, you pick up any one point a, let us say sigma a divided by epsilon a power n. So, sigma a is known to you 118.11 divided by epsilon a is 0.0392 power 0.12, it will give you 174.2 megapascal. It is near about 174 megapascal. Okay. But one should not use this equation so freely, but because we do not have any data, one can evaluate in this way. Okay. So, this is another easy problem one can think about, and then this one problem, it will take little longer to calculate, but then one can do it and check. This is a typical test data they have given. Third problem. Okay. So, you can see that the following data pairs, one is load, other one is extension, right. So, load, extension or displacement, you can say this is load, this is extension, you can say delta L. Okay. This fellow will be in mm, and this fellow they have given it in kilonewton. Okay. I am drawing like this. The data is given were obtained from plastic part of a load extension file for a tensile test on a extra deep drawing quality steel, EDDQ. It is called as EDDQ. Okay. There is a steel like that with a particular carbon composition, you can look into it, and it has got a thickness of 0.8 mm, and the initial test piece has got a width of 12.5, gauge length 50. See, this is standard dimensions everywhere we are using. No? 50 is a gauge length, that is what I was telling you before, and 12.5 is the width of the gauge region, and thickness can vary. This is a standard dimension. So, this could be your load and this could be your extension, right. So, you start from 0.08, this is the load, 0.76, this is the load, 1.85, this is the load. So, it will keep on increasing in this way, right. So, all are given here. So, now the question is what they are asking is you have to get the this is continuing 2.98, 8.92 and 2.93, 11.06. Okay. So, it is continuing here, okay, and you can see 1.9, 1.85, it is increasing 2.57, 2.9, 2.93, 94, 9, this 92, this could be we have to check this. Okay, anyway, this is 2.x. You can neglect this data point also. You can directly 2. Okay, fine, it's fine. It's decreasing. 9.4, then 9.2. Okay, then you have 16.59. Okay, then 8.6. Okay, then 2.61, 2.18. You have 22.69. Okay, so it's basically you have to get the engineering stress strain behavior, true stress strain behavior, then log stress, log strain curves. Okay, and from this you can get yield strength, UTS, true strain at maximum load, and then your K and N. Okay, this is a typical test data you have, and from here you can get all the data. Okay. So, we have just roughly calculated it. Okay. So, what you need to do is basically you need to get engineering stress strain curve first. Okay. I think if you know load extension data, so then from here you can get engineering S versus E. Okay. Load divided by initial area of cross section. From this initial area of cross section is known to you, right? 0.8 into 12.5 you can put. Load is already given, and your load versus engineering strain. Engineering strain you can put in decimals, which is nothing but delta L by L naught. Delta L is already given and L naught is 50. So, you get engineering stress strain curve, that is found out, and from engineering stress strain curve you can get 2 stress strain curve, or from that you can directly get this also. Okay. Because your P is known, P is already given, and then you need to get instantaneous area of cross section. For that you can get A naught L naught is equal to AL. So, A naught L naught divided by L will be your A, right, will be your A. So, that A, this entire thing will give you your sigma. Okay. And here also your L can be obtained from delta L, because initial gauge length L naught is known to you. So, you can get L. So, you can get A, this can be obtained, and this fellow epsilon is nothing but ln of L by L naught. So, L naught can, anyway you know here you can get, you can put 50 here and you can get epsilon. Okay. So, that will give you true stress strain data, and true stress strain data directly you can get logarithmic of stress and strain curve. Generally it is a straight line, and from here you can get initial yield stress. It is also given obtained from the plastic part of the load extension file, which means that there is no elastic part. So, which is comfortable for this, because the first data point itself can be assumed as your initial yield stress, which is what is to some extent we have calculated here. You can see this is the engineering stress strain behavior. Okay. The first data point here, and true stress strain behavior is also evaluated, and the slope is also evaluated here. Okay. You can just check it. Okay. So, your yield strength is how much is coming is 156 megapascal. Okay. So, 156 megapascal is somewhere closer to here, you can see this closer to this, slightly less than 160 you have, isn't it. So, you have 156 megapascal. Ultimate tensile strength, that is your UTS. So, you can just check your engineering stress strain graph. UTS means you have to go to engineering stress strain graph, because that has got a maximum stress. So, you can see that is about, probably this could be somewhere here. So, you have to accurately get it. Once you draw this graph you will know. So, which is nothing but 294. True strain at maximum load. Okay. So, what does it mean? True strain at maximum load means, what does it mean? Okay. So, like whatever maximum load, that is UTS, is reached, corresponding to that you get engineering strain and convert that into true strain. So, this is engineering strain. Okay. E, you should convert that into engineering true strain, nothing but ln of 1 plus E, like that you can convert. That will give you true strain value. Okay. Total elongation is about, we say 45.4%, we are saying 45.4, you can say that near about 45, you can see that total elongation is generally up to full fracture, no. So, you can say about 0.45 is coming here. So, which is nothing but in percentage 45.5, 45.4. Okay. And K value and N value can be calculated like the way we discussed in the previous problem. Okay. N value you know now. So, okay. So, N value can be calculated directly from the slope of the logarithmic plot, which already drawn now, which is, for example, is given here. You can check it. Okay. So, probably you need to leave this initial point, because there are actually 2 slopes. Just be careful. Pick up a point where you have one slope and then get N value, and from there onwards you can get a K value. Okay. You can just check it. Okay. So, this is a long problem. One has to actually use a graph paper and then Excel sheet or something like that, and then you can calculate it properly. This will help you to do that. Okay. So, these 3 problems will help you to understand what kind of calculations that we make for the second part of the first chapter, that is your tensile test. Okay. So, with this we will stop this chapter. We will start the next chapter in the next portion. So, what we have done essentially in this is basically introducing the sheet forming process, and then tension test, which is a very basic test used for characterizing the sheet material properties, mostly mechanical properties, and those are required to give as input to your modeling. Okay. So, in that way we know load displacement graph, then engineering stress strain graph, true stress strain graph, calculating all the properties including K and N, and then M, strain rate sensitivity index, and then there's a separate section on calculating plastic strain ratio, which quantifies anisotropy of the sheet. Okay, some standard method of doing it, and then in problem also we did some little calculation in one of the problem to how to get R value. And then finally a small part is discussed in how N, yield strength, your elongation, R value, M, then surface roughness, then let us say homogeneity, okay, and then these are some important quality of a sheet that is going to affect the forming behavior. So how it can affect elastic modulus, that also we have seen. Okay, so it's better to have larger N and M to have better formability generally, and R bar is better, larger is better because you have large resistance to thinning and you can make deeper components. Delta R should be small to avoid earring problem. Okay, and then M, it's better to have larger M to have large ductility. And then the surface roughness, generally it plays a little role in evaluating the final components performance. And then strength, okay, so that actually decides the stiffness of the component, that's the only thing. Then elastic modulus is going to control the spring back of the sheet. In one way it is going to affect the spring back of the sheet, which also should be as minimum as spring back should be minimized, and accordingly you have to choose the material's Young's modulus. Okay. So just to summarize, this is what we have done, and then we will move on to next chapter in the next class.